In today's video, we're going to look at what exothermic and endothermic reactions are, see how we can represent them using reaction profiles, and finally, consider the importance of activation energy. Now, the important concept to understand in this topic is that different chemicals store different amounts of energy in their bonds. For example, if we took the reaction methane plus oxygen goes to form carbon dioxide and water, then each of these different molecules would hold a different amount of energy. Or in other words, they'd each have different amounts of energy in their chemical energy stores. What's important to us, though, is how much energy all of the reactants have in total, compared to how much energy all the products have in total. In this particular case, the products would have less energy than the reactants. And we can show this on a reaction profile, where the y-axis is the total energy of the molecules, and the x-axis is the progress of the reaction. So on the left, we place our reactants, and on the right, we put our products. But importantly, for this reaction, we'd have to put the products lower down, because they have less energy. Now, if the chemicals in the reaction have lost this much energy, then this much energy must have been released to the surroundings. Because remember, energy can't be created or destroyed. It can only be transferred from one place to another. And the most common way to exchange energy with the surroundings is in the form of heat. In this reaction, lots of heat energy would be released. So if we had done it in a sealed container, then we'd be able to measure the increase in temperature as the reaction progresses and releases heat energy. We call reactions like this exothermic. And what all exothermic reactions have in common is that they transfer energy to the surroundings, usually in the form of heat. The most common type of exothermic reaction is combustion reactions, in which fuels are burned, usually in the presence of oxygen, like in our reaction. Other examples, though, include neutralization reactions between acids and bases, and most oxidation reactions. The opposite of an exothermic reaction is an endothermic reaction. These are reactions which take in heat energy from the surroundings. For example, if we wanted to break down calcium carbonate into calcium oxide and carbon dioxide, we'd have to supply heat, perhaps by using a Bunsen burner to heat up the solid calcium carbonate. So if we wanted to draw a reaction profile for this reaction, then just like before, our reactants would be on the left, and the products on the right. But this time, the products would be higher up, because they have more energy than the reactants. And so we'd label this difference as the energy absorbed, rather than the energy released. So far, we've covered what exothermic and endothermic reactions are, and looked at the reaction profiles for each, which you might have to draw in the exams. The last thing we need to cover is activation energy, which is the minimum amount of energy the reactant particles need in order to collide with each other and react. So the greater the activation energy, the more energy that will be required to start the reaction. We can show this activation energy on our reaction profiles when we draw a curve from the reactants to the products to show how the energy changes during the reaction. Specifically, this increase in energy from the reactant's energy level to the highest point on our curve is the activation energy. So as you can see, even in an exothermic reaction like this one, which releases energy overall, some energy is still required to get the reaction going in the first place. We can do the same thing for endothermic reaction profiles. Again, we draw our curve, and the activation energy will be the difference in energy between the reactant's energy level and the very top of our curve. This means that if we wanted to show the same reactions, but with slightly higher activation energies, then we'd just make our curves go a bit higher. Whereas if we wanted to show lower activation energies, we'd just make them a bit lower. Now, the very last thing we need to say is that if you were drawing a reaction profile for a specific reaction, like the ones that we discussed earlier, then instead of just writing reactants and products on the lines, we can actually put the chemicals from our equations. Anyway, that's